Bismillahirrahmanirrahim. Assalamu alaikum students. It's chapter 28, magnetic fields. As we have discussed that one major goal of physics is the study of how an electric field can produce an electric force on a charged object. A closely related goal is the study of how a magnetic field can produce a magnetic force on a charged particle or on a magnetic object such as magnet. So in this chapter we are going to study and we are going to deal with all magnetic field related problems. The topics we are going to study in this chapter are crossed fields, that are discovery of the electron, the Hall effect, magnetic force on a current carrying wire, and torque on a current loop. Defining magnetic field. Students, we know that an electric field is produced by an electric charge. In a similar way, we can expect that a magnetic field is produced by a magnetic charge. Although individual magnetic charges called magnetic monopoles are predicted by certain theories, their existence has not been confirmed. Then how are magnetic fields produced? There are two ways. One way is to use moving electrically charged particles such as current in a wire to make an electromagnet. The other way to produce a magnetic field is by means of elementary particles such as electrons, because their particles have an intrinsic magnetic field around them. That is, the magnetic field is the basic characteristics of each particle, just as mass and electric charge. Our first job in this chapter is to define the magnetic field B, and we do so by using the experimental fact that when a charged particles move through a magnetic field, a magnetic force F acts on that particles. The definition of B: basically, a magnetic field is the vector quantity. The direction of the magnetic field at any location is the direction in which a compass needle points at that location, and like electric field, we can represent the magnetic fields by means of drawing magnetic fields lines. We know that the electric field at a point electric field can be determined as a point by putting a test charge of charge Q at rest at that point and measuring the electric force acting on the particle, and we use the formula E is equals to F by Q. If for example magnetic monopole were available, we can define B in a similar way. Because such particles have not been found, we must define B in another way in terms of the magnetic force exerted on a moving electrically charged test particles. We can quantify the magnetic field by using our model of a particle in a field. The existence of a magnetic field at some point in space can be determined by measuring the magnetic force exerted on an appropriate test particle placed at that point. If we perform such an experiment by placing a particle with charge in the magnetic field, we define the following results that are similar to those for experiments on electric forces. The magnetic force is proportional to the charge Q of the particle. The magnetic force on a negative charge is directed opposite to the force on a positive charge moving in the same direction. The magnetic force is proportional to the magnitude of the magnetic field vector B. We can also find the results which are totally different from those for experiments on electric forces. The magnetic force is proportional to the speed v of the particle. If the velocity vector makes an angle theta with the magnetic field, the magnitude of the magnetic force is proportional to sine theta. When a charged particle moves parallel to the magnetic field vector, the magnetic force on the charge is zero. When a charged particle moves in a direction not parallel to the magnetic field vector, the magnetic force acts in a direction perpendicular to V and B, that is, the magnetic force is perpendicular to the plane formed by V and B. These results show that the magnetic force on a particle is more complicated than the electric force. The magnetic force is distinctive because it depends on the velocity of the particle and because its direction is perpendicular to both V and B. These observations can be summarized in a compact way by writing the magnetic force in this form: Fb is equals to Qv cross B, which is defined by the cross product, and it is perpendicular cross product of V and B, and it is perpendicular to the both V and B. Finding the magnetic force on a particle. This equation Fb is equals to Qv cross B tell us that the magnitude of the force acting on a particle in a magnetic field is proportional to the charge Q and speed v of the particle. Thus, the force is equals to 0 if the charge is 0 or if the particle is stationary. It means if the particle is not moving, then its velocity will be equals to 0, then the force Fb will be 0. This equation also tells us that the magnitude of the force is 0 if velocity of the particle and magnetic field are either parallel or anti-parallel, and the force is at its maximum when V and B are perpendicular to each other. The right hand rule tells us that the thumb of the right hand points in the direction of V cross B, that is the cross product of two vectors V and B. When the fingers sweep V into B, the thumb will point in the direction of V cross B, that is the direction of force. If Q is positive, if your charge is positive, then the force Fb has the same sign as V cross B, and thus it must be in the same direction, that is for positive Q. If Q is negative, then the force Fb and cross product V cross B have opposite signs and thus must be in opposite direction. For negative charge Q, Fb is directed opposite to the thumb. You can see in this figure. These three figures are for positive charge. Cross V into B to get the new vector V cross B. If you cross your palm represent the normal to your palm represent the direction of magnetic field. Your fingers represent the direction of velocity. If you cross V into B, the thumb will point in the direction of force. For positive charge, it is it is the situation, and for negative charge the force will be exactly opposite to this force. It means if for positive charge force is in the upward direction, then for negative charge the force will be in opposite direction. If for a positive charge the force is in upward direction, for negative charge it will be in downwards direction. These two figures showing force on a this figure is showing a force on a negative particle. It is in the downward direction, that is opposite to the force which is on positive particle. And the force acting on a charged particle moving with velocity v through a magnetic field B is always perpendicular to V and B. And this magnetic force never has a component parallel to V. This means that Fb cannot change the particle speed V. The force can only change the direction of V. Only in this sense can Fb, the magnetic force, accelerate the particle.